stream 2, these two streams are mixed, and let us say that this is the condition of the exit stream. Okay. So, you can point the composition, this is the composition of the stream 1, composition of stream 2, and this is the composition of stream 3. Similarly, enthalpy, this is the enthalpy of stream 1, enthalpy of stream 2, and enthalpy of stream 3. Okay. And you will find that it can be easily shown, I will show you in a minute, that this distance is nothing but m2 by m3, and this distance is nothing but m1 by m3. Okay. How do you do that? Okay. So, let me show this again on it. Yeah, so I will show these equations. If you are applying mass and energy balance, then you know that from mass balance m1 plus m2 should be equal to m3. This is the total mass balance. Okay. You can also write a mass balance for ammonia, right. So, m1 zeta 1 plus m2 zeta 2 is m3 zeta 3, and this is the energy balance for the adiabatic mixing chamber. Okay. So, no heat transfer, no work transfer. So, the composition enthalpy of the mixer at the exit of the mixing chamber, for using these equation and eliminate m1, you can easily show that the mixer condition, the composition is given by this and the enthalpy is given by this simple equation. Okay. So, from that you can easily show that this mixer condition, these distances are m2 by m3 and m1 by m3. For example, as m2 increases, you will find that this point as m2 by m3 increases, this point will shift to this side. That means the exit condition will be moving closer to 2. Similarly, when m1 increases, this point will shift in this direction and the mixer condition will be 1. If m1 or m2 is 0, then you will find that this condition coincides with 1 or 2. Okay. Now, if the streams are such that the mixing condition is in the two phase region, then what do we do? For example, let us say that we have mixed two streams where stream 1 is a saturated liquid and stream 2 is a subcooled liquid. Okay. So, these two streams are mixed, and you will find that the resultant mixer, that means the outlet mixer, lies in the two phase region, because as you know that the outlet condition must lie on a straight line joining point 1 and 2. Okay. So, this is the mixing process. So, the outlet condition must lie on point 3. So, when you are pointing it out on this, knowing m1 m2, and if you are finding that this point lies in the two phase region, okay, then we do not know this temperature. Okay. And two phase region means again it will have vapor and liquid phase mass fractions. Again this temperature as well as vapor and liquid phase mass fractions have got to be obtained from trial and error method, as I have explained earlier. Okay. And it can be easily shown that the fraction of vapor in the mixer at 3 in two phase region, okay, in two phase region is given by this expression. That means, this is the mass of vapor to the total mass, this is nothing but your dryness fraction, and this should be L. Okay, 3L zeta 3 minus zeta 3L by zeta 3V minus zeta 3L. Okay, so this is nothing but your dryness fraction. Okay. So, if you know these points, then you can easily find out the dryness fraction, and geometrically you can find out once you get these lengths. Now, let us look at another process where mixing of two streams takes place with heat transfer. Okay. This is a typical process that takes place either in the absorber or generator of absorption refrigeration systems. Okay. So, let me show that process. Okay. So, this is similar to the earlier one, only difference is here you have heat transfer. Okay. So, again stream 1 is mixing with stream 2, and the resultant mixer is stream 3, and during this process some heat has been transferred. Okay. If it is an absorber, you know that it is an exothermic process, so heat is transferred out of the system. If it is generator, you have to supply heat to the system. Okay. Let us say that this is the process. For this process, what are the steady flow equations? Steady flow equation, just like earlier this thing, mass balance is this, total mass balance, this is the mass balance for ammonia, okay, and this is the energy balance. Okay. So, the only difference between the adiabatic mixing and mixing with heat transfer is in this term. When this Q becomes 0, you will find exactly this equation is exactly same as adiabatic mixing process. When Q is non-zero, you get this equation. So, from this equation it can be very easily shown that the exit enthalpy H3 is nothing but H1 plus M2 minus H3 into H2 minus H1 minus Q by M3. So, this is the difference. Okay. So, the same thing can be easily shown on your concentration enthalpy diagram like this. Without any mixing, this will be the process. Okay, I am sorry, without any heat transfer, this is the process. With heat transfer, you will find that the exit condition lies at a vertical distance below this point if heat transfer is from the system. Okay, and this distance is nothing but the heat transfer rate divided by the mass flow rate of the solution at condition 3. Okay. So, if you know these two things, first find out this point assuming that it is adiabatic mixing, then this point is simply assumed simply obtained by drawing a vertical line and going down by this much distance. Okay. That means this is without any heat transfer, H3 dash is the specific enthalpy and H3 is enthalpy with heat transfer from the system. Okay. If the heat transfer is to the system, obviously this point will move up. Okay. This is for the positive Q, whereas this is for the negative Q. Okay. So, with heat transfer from the mixing chamber, the exit state lies at a vertical distance of Q by M3 below or above the state which would result without heat transfer. That is what I have explained just now. Now, let us look at another simple process, that is the throttling process. As you know, throttling takes place in the solution expansion valve of the absorption refrigerant system. Okay. So, throttling is an isenthalpic expansion process, and during this process there is a possibility of vapor generation due to flashing. Okay. This we have seen earlier. If this is the case, then you will find that the exit condition lies in the two phase region. If the exit condition lies in the two phase region, again you have to use a trial and error method to find the exit temperature and vapor fraction. Okay. So, let me quickly show the throttling process. Okay. So, as you know, this is the throttle valve. So, a solution at condition 1 passes through the throttle valve and it emerges out at point 2, and if the pressure P1 is at condition 1 and if P2 is at the exit, and you know that P1 is greater than P2. Okay. And this is typically an isenthalpic process. So, there is neither heat transfer nor work transfer during this process. So, if you are applying mass and energy balance, you will simply find that the composition remains constant and the enthalpy also remains constant. So, if you are trying to show this throttling process on enthalpy composition diagram, you will find that both inlet and exit points are on the at the same point. Okay. That means they are identical. Okay. Why they are identical? Because enthalpy is also same as this equation shows, and concentration is also same, right. So, they will be identical, but we know that at this point the pressure is different, and if there is any vapor generation, the temperature also will be different. That means pressure is will be lower than outlet pressure will be lower than inlet pressure. Similarly, outlet temperature will be lower than inlet temperature. Okay. So, how do we find these outlet and inlet pressures? We know that this exit condition, for example, point 2, it is a mixture of saturated liquid plus saturated vapor at outlet pressure P2. Okay. That means suppose this is the saturated liquid condition and this is saturated vapor condition at the outlet pressure P2, and if you know these by trial and error method, then you can find out the temperature. Okay. Because this temperature is nothing but the temperature of this isotherm. Okay. So, this is how we have to find the exit condition of the throttling process. Now, let us look at another simple but important process, that is called heating and cooling process. So, let me first explain the arrangement. Okay. What we have here is an arrangement which consists of two heat exchangers, heat exchanger A and heat exchanger B, and also two separators, separator A and separator B. Okay. So, initially I have taken a subcooled solution. Okay. This is a subcooled solution, remember, and here pressure is constant everywhere. So, I have taken a subcooled solution at state 1 and I have heated that subcooled solution in a heat exchanger A by supplying heat 1 Q2. Okay. So, heat is supplied and this comes out at point 2. okay, and this heat supplied is such that point 2 lies in the two phase region. That means at point 2 you have both liquid and vapor. Okay. Then what is done is this liquid and vapor two phase mixer is fed to the separator A. In the separator, the saturated liquid at state 3 is separated from saturated vapor at state 4. So, this is the saturated vapor. Okay. That means separator, what is the function of separator? Function of separator is simply to separate the liquid from the vapor, okay, at the same pressure, and there is no heat transfer or anything in the separator, that is the assumption. So, here we are separating out the saturated liquid and vapor. Then here you have saturated vapor, and what we are doing is I am cooling this saturated vapor in this heat exchanger B by extracting this much amount of heat. Okay. So, first the solution is heated in heat exchanger A, and liquid and vapor are separated in separator A, and then the saturated vapor is cooled in heat exchanger B by rejecting heat to outside. Okay. And it is cooled in such a way that this condition again lies in the liquid and vapor phases. Okay. So, these heat transfer rates should be in such that at the exit of heat exchangers you have two phase region. Okay. So, again I am using another separator B where I am separating out the liquid from the vapor. So, finally I am taking the vapor from the arrangement at this point, saturated liquid at this point, and saturated liquid at this point. So, this is the arrangement. Okay. Suppose I am plotting this process on enthalpy composition diagram. How does it look? Okay. So, we have started with subcooled liquid at state 1, and we have heated this in heat exchanger A. So, this is your heat exchanger A. Okay. So, since this is a single stream, you know that the exit condition will lie simply at a vertical distance of 1 Q2 by M1 above this point. Okay. So, I can easily find out this enthalpy, and during this process your concentration remains same. Okay. So, zeta 1 is equal to zeta 2 during this process, right, but the point 2 lies in the saturated lies in the two phase region. Okay. This is the liquid plus vapor region. So, that means at this point you have saturated liquid at point 3 and saturated vapor at point 4. Now, if you look at the earlier diagram, what we have done is at this point we have taken out the saturated liquid and saturated vapor from the separator A. Okay. So, this is the process occurring in separator A, and from that point onwards what is done is this saturated vapor, okay, at condition 4 is cooled in the heat exchanger B. Okay. So, this is the process in heat exchanger B. Since this is cooled sensibly, I mean this is cooled by rejecting heat to the surroundings, you find that the exit condition lies at a vertical distance of 4 Q5 by M4 below this point. Okay. So, you can again easily find out this one if you know this and if you know this. Okay. Similar to this, if you know this you can find out this point. So, we have got the point 5. At this point again this is in two phase region. So, again you have a mixture of saturated liquid at point 6 and saturated vapor at point 7. Okay. And at this point the vapor is taken out. Okay. So, what is that we have done during this process? What we have done during this process is we have taken subcooled liquid. Okay, we have taken subcooled liquid at this point, and we are getting a vapor, okay, that is rich in ammonia. Okay. Suppose this process is continued further. Okay, you will find that as you are you have taken again this vapor, and this vapor is again cooled. Okay. And you have separated out again the liquid and vapor. So, you can see that this point, that means the outlet point, progressively moves closer to the pure ammonia state. That means you are getting vapor that is rich in ammonia at the exit of this arrangement. Okay, that means the whole system is working like a rectification column. So, that means I have used a combination of two heat exchangers and two separators, and I have started the process with a subcooled liquid. I have heated the liquid, then I separated the saturated liquid and vapors, then I cooled the saturated vapor, again I separated the liquid and vapor fractions, and finally I have a rich ammonia vapor. Okay, rich vapor vapor that is rich in ammonia. Okay. So, this is actually the purpose of any rectification system where you feed the liquid and you get pure components. right. Now if you apply the simple mass and energy balance for these components, for example for the heat exchanger, as I explained, total mass is conserved, concentration remains same. So, this is the energy balance, okay. This is the heat supplied is utilized for increasing the enthalpy, okay, and this is the mass flow rate, okay. And similarly mass and energy balance for the separator. In the separator, this is the total mass balance, that means whatever mass is coming in is mass going out in liquid form and in vapor form. Similarly, you can write mass balance for ammonia, okay. So, this is the amount of ammonia entering into the separator A, and this is the amount of ammonia leaving the separator A, okay, in liquid form, again in vapor form, and this is the energy balance for the separator, no heat transfer or work transfer. So, this is simple energy balance for the separator, okay. So, similarly a set of equations can be written for heat exchanger B and separator B also, okay. For these two also you can write similar set of equations. From these equations you can show that M3 by M2 is nothing but zeta 4 minus zeta 2 divided by zeta 4 minus zeta 3, okay, length 4 2. This is nothing but your mass fraction, liquid phase mass fraction. Similarly, this is the vapor phase, I mean liquid, this is the ratio of mass of saturated liquid to the total mass in separator A, and similarly this is the ratio of saturated vapor to the total mass in separator B, okay, and ultimately they can be expressed in terms of the different lengths, okay, which are shown in the earlier diagram. So, if you can draw the diagram, you can easily find out how much liquid you have, how much vapor you have, and as I said, you can write similar equations for heat exchanger B and separator B. Okay. So, as I said, from the arrangement consisting of heating, cooling and separation, one finally obtains vapor that is rich in ammonia. Okay. So, this process is similar to rectification. So, in this case heat exchanger A plays the role of generator, while heat exchanger B plays the role of a component called deflagrator. Okay. However, in actual systems just a generator and deflagrator are not sufficient. So, we also use a rectification column which is introduced in between generator and deflagrator. This is required to improve the process of rectification. Okay. So, an actual absorption refrigerant system based on ammonia water will have the generator, a rectification column and a deflagrator. Okay. And the principle is what we explained just now. Okay. So, I will explain the basic system consisting of all these components and the working principle in the next class. So, let me quickly summarize what we have learned in this lesson. So, in this lesson systems based on ammonia water are introduced and properties of ammonia water are discussed with reference to composition in liquid and vapor phases, vapor pressure and enthalpy data, and some simple processes using mixers are analyzed assuming steady flow process. Okay. In the next class I shall discuss the actual systems. Okay. Thank you.